welcome to today's deep dive. If you're joining us, well, it's because you're that ever-curious learner who just loves falling down a really fascinating rabbit hole.
Oh, absolutely.
You know the feeling. You start off looking for a simple answer to a very specific problem, and suddenly you are uncovering an entire hidden world of context.
It happens to the best of us.
Right. Well, today, we are embarking on a very special mission. We're looking at a hyper-specific blog post from February 27th, 2026. It is titled, Notes on Haskell Programming Part 69, Test Breakdown of ParserResult with Print.
Which, I mean, let's be honest, that sounds incredibly niche at first glance.
Very niche.
But that specificity is exactly what makes it so valuable for us to explore today. We aren't just going to look at the mechanics of Haskell code, although we will definitely get into the weeds of how this specific parser functions.
Yeah, we're actually using this single post as a window into the mind of its author. His name is Kian-Meng Ang, and on his site, he describes himself simply as an old software plumber.
I love that phrasing.
Me too. And okay, let's unpack this a bit, because setting the scene here is crucial. This isn't just your standard tech blog where a developer drops a tutorial once every 6 months to keep their resume looking fresh.
Not at all.
You're looking at a massive, sprawling 15-year digital archive.
And the sheer volume of his output, it completely recontextualizes this single post about a Haskell test. If you look at the archive spanning from 2011 to 2026, you see a level of discipline that, frankly, borders on the monumental.
It's wild.
In the years leading up to this post, so 2022, 2023, 2024, 2025, he was consistently publishing over 700 posts annually, every single year.
That's roughly 2 posts a day, every day, without fail.
Yeah.
And by early 2026, and remember this post was published in late February, he'd already published nearly 190 posts for the year. Just stop and think about that output for a second.
It's staggering.
Imagine sitting down to document your work, your thoughts, your troubleshooting twice a day, every single day, for years on end.
What's really fascinating here is the broader context that surrounds this single Haskell post. When you glance at the sidebar of his site, you quickly realize this old software plumber isn't just plumbing code.
Oh, definitely not. That sidebar is actually my favorite part of this entire archive.
Right. Alongside notes on Python, notes on Rust, notes on Go, and notes on AI, he is meticulously logging the physical, organic world around him with that exact same rigor.
You're scrolling through deep technical content about functional programming, and right next to it is notes on gardening, which is up to part 821, by the way.
Part 821.
He's writing about why your mint isn't growing, the intricacies of propagating Brazilian spinach, figuring out phosphorus deficiencies, and documenting his battles with mealybugs.
It's incredible.
He even has notes on fish keeping, up to part 202, exploring whether duppies eat algae and maintaining specific beta spawn logs. He logs his photography, his meditation, dieting, home improvement projects.
And if we connect this to the bigger picture, it says something really profound about the fundamental learner mindset. For you, the listener, whether you're architecting a new software platform or just trying to pick up a new language, this reflects a universal system for problem solving.
Exactly.
Documenting seemingly unrelated hobbies, like debugging a complex Haskell parser on one hand and figuring out why a variegated plant is losing its color on the other, is ultimately the exact same cognitive exercise.
They both require a system of deep, careful observation.
Precisely. It's about taking a system, whether organic or digital, watching how it behaves under specific conditions, and carefully logging the variables. He's applying the scientific method to every aspect of his daily life, and he's making those logs completely public.
Which brings us perfectly to his core philosophy. You look at his DOS support list on the blog, and it completely aligns with this mindset. He urges his readers to support the Electronic Frontier Foundation, the Free Software Foundation, the Tor Project, and Wikipedia.
He's a dedicated advocate for FLOSS, free, Libre, and open source software. And that ethos of open information explains his impulse to share every single step of his learning journey with the open internet.
Yeah, he isn't keeping his solutions locked away.
Right. Whether it's an Elixir library workaround or a method for identifying root knot nematodes, he operates on the belief that knowledge builds on itself when it's shared openly. Just putting it out there.
So keeping that Renaissance plumber mindset in focus, let's dive into the actual catalyst for this specific post. This is part 69 of his notes on Haskell Programming. In this post, he's trying to do something that sounds incredibly fundamental. He's adding a new test to see how his parser handles a very common edge case, a missing input file.
And before we talk about the failure, we should probably clarify why testing for a missing file is a crucial step in parser design. A parser's entire job is to take raw, chaotic input like user commands or text files and turn it into structured data that the program can actually use.
Right, so if you're building a command line tool, you're expecting the user to point the tool at a file. But what if they type the file name wrong? Or what if the file just got deleted?
Exactly. A missing file is the ultimate wrench in the gears. A good program shouldn't just crash and burn when that happens. The parser result is designed to elegantly capture that scenario and return a helpful message. So he builds a test specifically to trigger this missing file scenario and ensure the parser handles it gracefully.
But the console app completely failed to handle it.
Yep.
And threw an unhandled exception and broke. And here's where it gets really interesting and so relatable for anyone who has ever tinkered with a system. You build a test, the system immediately breaks. And instead of panicking or jumping into the source code to patch the app, he just casually writes, "But we'll discuss that in following post."
He completely shelves the actual fix.
He uses the failure as an excuse to just refresh his memory on his own test code.
And this raises an important question. Why step away from the broken application code to look at the test itself? To an amateur, that sounds like procrastination, but it's actually a brilliant practice. Stepping back from a broken system to fundamentally understand the tools you're using to test it is a hallmark of an experienced plumber.
Checking your wrench before you fix the pipe.
Exactly. When the pipe bursts, you don't just blindly start patching the hole. You check your wrench. You check the water pressure gauge. You make sure your diagnostic tools are giving you an accurate, reliable reading before you attempt the actual repair. He's verifying his test harness.
Okay, let's unpack this test code he's looking at because it gives us a really accessible look into Haskell's architecture. He mentions a helper function called runFullParser, and he notes that it returns an I/O type, specifically I/O containing a ParserResult args. Now, for you listening, I want to use an analogy here. Think of I/O like a heavy steel shipping container. The ParserResult is the actual cargo inside, the result you want, but it's locked inside this container, which represents the messy, unpredictable outside world of input and output.
That's a highly useful analogy, especially because Haskell is a purely functional language. Unlike Python or JavaScript, Haskell hates hidden side effects.
It really does.
It doesn't want your code secretly talking to the outside world, like reading from a file system or printing to a screen without explicitly declaring it. The I/O container is Haskell's way of safely quarantining those messy real-world interactions away from the pure mathematical logic of the rest of the program.
So you can't just casually grab the result out of that I/O container whenever you feel like it. It demands a specific, secure process.
Correct. The author explains that he uses the left arrow bind, that's the less than sign followed by a hyphen, to extract the result from that I/O container. You have to explicitly command Haskell to unpack the shipping container before you can examine the cargo inside. Once he uses that bind to pry open the container, he pattern matches the result using a case statement. He's basically looking at the cargo and saying, okay, in the case that it's this type of result, I do X. In the case that it's a failure, I do Y.
Right.
And during this breakdown, he casually drops a line about something called pure open parenthesis, close parenthesis. Just an open and closed parenthesis with nothing in between. He says it simply means do nothing and finish successfully.
Let's pause on that concept because it often trips people up. If you're coming from languages like Java or C, you might be tempted to equate those empty parentheses to a null pointer or a void return.
That was my exact instinct when I read it. It looks like it's just handing back a big, dangerous nothing.
It's a very common trap, but it's fundamentally different. Null is the dangerous absence of a value. It's a missing pointer that can crash your program if you try to read it. But in Haskell, those empty parentheses represent the unit value.
A unit value.
Yes, unit is a perfectly valid concrete type that has exactly one value. So it's not a missing puzzle piece. It's a puzzle piece that is intentionally perfectly blank.
That's a great way to put it. It's a deliberate structural placeholder. It tells the program the action occurred, the container was processed, but there is no meaningful data to hand back to you. It highlights the rigorous structure of Haskell. Every single branch of logic, even one that yields no actionable data, must be explicitly defined and accounted for.
So what does this all mean when you're actually trying to debug a broken test? Because remember, his app failed to handle the missing file, and he wants to see exactly what the parser is spitting out before it crashes.
Yeah.
He pivots to a specific debugging trick for his readers. He says if you want to see the actual result during a test, you just add a print statement.
Which sounds simple enough, but in Haskell, you can't just dump raw internal data structures directly onto the screen. To accomplish this, he mentions relying on the show function.
Because the terminal only understands text, right?
Yeah, exactly. The show function serves as a translator. It takes that complex internal ParserResult data structure and converts it into a readable string format. Once it's converted to a string, it can be visibly printed to the console when he runs his test suite.
He mentions running the stack test command. And for context, stack is just a cross-platform build tool specifically designed for Haskell projects. It handles the dependencies and runs the test suites.
Right.
So he runs stack test, it triggers the print statement, and he shares the resulting output in the post. And looking at this output, it's incredibly structured. It's not just a messy stack trace.
When he dissects what the output actually reveals, he points out the ParserFailure data constructor. This is what I meant earlier about handling errors gracefully. This isn't just a generic error 404 or some vague red flag.
No.
The ParserFailure acts as a neatly organized package. It holds the specific error message, the usage instructions for the user, and the overarching help text.
It provides a complete map of what went wrong and how the user is supposed to interact with the program correctly. But the real aha moment for me, the part that genuinely made me smile, was at the very end of this parsed output.
Oh, the numbers.
Yes. After all the complex error messages and help text strings, the output just simply reads 1,80.
That tiny detail is surprisingly rich with history. He breaks down what those two numbers represent. The 1 is the exit code for the error, elegantly bundled right into the failure object. But the 80 represents the terminal width used for wrapping the help text.
80 characters. It's such a hyper-specific number to see hard-coded into a modern programming test in the year 2026.
If we look at the historical elegance of that 80-character terminal width, it connects this tiny, obscure debugging detail to the broader legacy of computer hardware and software design. The 80-character limit isn't arbitrary. It dates back decades, all the way back to IBM punch cards.
Wait, the actual physical cardboard cards used to program early mainframes?
Exactly. Those physical punch cards were designed with exactly 80 columns across. When you punched a hole, it represented a character or command. Because that physical hardware limitation became the industry standard, it completely dictated the design of early video terminals.
Wow.
When engineers built the iconic VT100 monitors in the late 1970s, they designed them to display exactly 80 characters across, mapping directly to the legacy of those punch cards.
So even today, when developers have massive, ultra-wide 4K curved monitors sitting on their desks, the ghost of an old cardboard IBM punch card is still quietly shaping how error text wraps in a modern Haskell console application. That is incredible.
It's a powerful testament to the layered history of technology. Our old software plumber isn't just dealing with abstract logic floating in the cloud. He's interacting with the physical, tangible history of computing, which has been preserved in the default settings of modern developer tools.
Let's just zoom back out for a second and look at the journey we've just taken based on this single, hyper-specific blog post. We started with a missing input file that broke a routine test, that led us to unpack the heavy steel shipping containers of Haskell I/O types, explore the deliberate structural placeholders of the unit type, and ended up with us marveling at an 80-character text limit inherited from mid-century punch cards.
That's quite a ride.
And all of this is carefully, publicly documented by a guy who has spent the last 15 years equally obsessed with software architecture and the health of his Mint plans.
Which brings us to why this matters to you, the listener. It's so easy to fall into the trap of thinking that gaining knowledge is just about reading the final, polished textbook or delivering a flawless presentation at work. We often hide our messy process.
We really do.
But this deep dive proves that real mastery is about getting your hands dirty. It's about building something, watching it break, and taking meticulous, curious notes along the way. Whether you're troubleshooting a complex project architecture or just trying to figure out why your houseplants are losing their leaves, the process of rigorous observation is your most powerful tool.
You don't have to be writing functional Haskell code to be a plumber in your own life. You just have to be willing to open up the pipes, see how the water flows, and ask why it's leaking.
Exactly.
Which leaves us with a final thought to mull over today. Qianming Ang's massive 15-year blog proves that documenting your failures, like an unhandled missing file exception, is just as important, if not more so, than documenting your polished successes? What if the most valuable thing you could leave behind isn't a flawless finished project, but the messy step-by-step logs of every single time you had to stop, scratch your head, and ask yourself, wait, why did that just break?
That is a very provocative thought to leave on.
Until next time, keep digging, keep taking notes, and we'll catch you on the next deep dive.